Right now, as you listen to this, something is happening in the outer reaches of our solar system that will never happen again. Not in your lifetime, not in your grandchildren's lifetime, not in the lifetime of our civilization as we know it. An object that does not belong here, an object that was born around another star in another part of the galaxy, possibly billions of years before our own sun ignited, is sailing past Jupiter. It came from the void between the stars, traveling at a speed that no rocket we have ever built could match. It swept through the inner solar system, past Mars, swung around the sun, and is now heading back out into the darkness from which it came. It will never return, not to us, not to anyone we will ever know. It is leaving, and it is taking its secrets with it. But not all of them. Because over the past 9 months, humanity has thrown everything it has at this visitor. The most powerful telescopes ever built, spacecraft orbiting Mars, spacecraft heading to Jupiter's moons, a rover standing on the surface of another world, a satellite designed to hunt for exoplanets, an infrared observatory launched to map the entire sky, a solar probe flying closer to the sun than anything humans have ever sent. All of them, every last one, turned their instruments toward this one small frozen traveler from deep space. And what they found has changed the way we think about the universe. This is the story of 3I-ATLS, the third interstellar object ever detected by humanity, a cosmic messenger wrapped in ice and mystery, an ancient relic that may be older than most stars in the Milky Way, and the story of how the most important data about this visitor was captured, delayed, withheld, fought over, leaked, and ultimately revealed is one of the most extraordinary episodes in the history of modern science. My name doesn't matter. What matters is that you understand what happened, what we saw, what we almost lost, and what it all means. So settle in. This is going to take a while, and it's going to be worth every minute. Let's begin at the very beginning. Not the beginning of 3I-ATLS, we'll get to that. I mean the beginning of our understanding that things from other star systems can visit ours. For most of human history, we assumed that the contents of our solar system were ours. The sun, the planets, the moons, the asteroids, the comets, all of it formed together from the same primordial cloud of gas and dust about 4.5 billion years ago. It was a closed system, a family. Everything in our cosmic neighborhood shared a common origin, a common chemistry, a common birthday. The comets that occasionally graced our skies with their luminous tails, Halley's, Hale-Bopp, Hyakutake, were all members of this family. Some came from the Kuiper Belt, that ring of icy debris beyond Neptune. Others fell inward from the Oort cloud, a vast spherical shell of frozen leftovers extending halfway to the nearest star. But they all belonged to us.
The idea that an object from another star system might occasionally wander through our neighborhood was theoretically sound. Stars form in clusters. Those clusters are gravitationally dynamic environments. During the chaotic early epochs of planetary formation, young star systems eject enormous quantities of material, comets, asteroids, planetesimals, flinging them into interstellar space at speeds sufficient to escape their parent star's gravity entirely. Once ejected, these objects drift through the galaxy for millions, even billions of years. They are orphans, cosmic nomads. And occasionally, purely by chance, their random trajectories bring them close enough to another star to be detectable, if we happen to be looking at the right patch of sky at the right time. For decades, astronomers searched for these interstellar vagabonds. They calculated how many should be drifting through our neighborhood at any given time. The estimates varied wildly, from a few per decade to several per year, depending on assumptions about how much material gets ejected from young star systems and how fast it moves. But despite all the searching, despite all the predictions, no one had ever actually found one.
Until October 19th, 2017. That was the day Robert Weryk, an astronomer at the University of Hawaii, was reviewing data from the Pan-STARRS telescope on Maui when he noticed something unusual. A faint point of light moving against the background stars at a speed that didn't make sense for any known solar system object. Weryk calculated its orbit and realized, with mounting excitement, that the object was on a hyperbolic trajectory, an open-ended path that meant it wasn't bound by the sun's gravity. It had come from outside the solar system. The object was designated 1I Oumuamua, a Hawaiian word meaning a messenger from afar arriving first. It was small, probably a few hundred meters long. It was tumbling end over end. It had no coma, no tail, no sign of the outgassing it characterizes a comet. And it had an extremely elongated shape, somewhere between 6 and 10 times longer than it was wide. Some estimates suggested it looked like a cigar. Others said it resembled a pancake. The truth is, we never got a good enough look to know for sure. By the time we realized what it was, Oumuamua was already heading away from us at blistering speed. We had perhaps a few weeks of useful observation time before it faded beyond the reach of our instruments. And during those few weeks, Oumuamua did something strange. As it receded from the sun, its trajectory showed a slight but unmistakable deviation from what pure gravity would predict. It was accelerating, very slightly but measurably, as if something was pushing it. The most natural explanation for this kind of non-gravitational acceleration in a small body is outgassing. As a comet is heated by the sun, jets of sublimating ice act like tiny rocket thrusters, nudging the object off its purely gravitational path. But Oumuamua showed no sign of a coma, no visible gas, no dust. If it was outgassing, it was doing so invisibly. This is where things got interesting. Most planetary scientists proposed straightforward explanations. Perhaps the outgassing was dominated by molecular hydrogen, which is transparent and difficult to detect. Perhaps the object was made of exotic ice that sublimated without producing a visible coma. Perhaps there were other physical mechanisms at work, radiation pressure on an unusually thin, lightweight surface, for instance. But one scientist proposed something different, something that would make him the most controversial figure in astronomy for the better part of a decade. Avi Loeb, the chair of the astronomy department at Harvard University, suggested that Oumuamua's anomalous acceleration might be explained if the object was not natural at all. What if, he proposed, Oumuamua was an artifact of extraterrestrial technology,
A light sail, perhaps, a thin, flat structure designed to be propelled by the pressure of starlight. That would explain the non-gravitational acceleration without requiring any outgassing. It would explain the unusual shape, and it would, of course, be the most extraordinary discovery in the history of science. The reaction from the scientific community was swift, loud, and overwhelmingly critical. Loeb's colleagues accused him of sensationalism. They pointed out that natural explanations were not only sufficient, but far more parsimonious. The principle of Occam's razor, that the simplest explanation consistent with the data is probably correct, strongly favored a natural origin. Suggesting aliens, they argued, was irresponsible and distracted from legitimate scientific inquiry. Loeb, however, was unmoved. He wrote a best-selling book. He gave hundreds of interviews. He founded the Galileo Project, a privately funded initiative dedicated to the systematic search for evidence of extraterrestrial technology. And he waited for the next interstellar visitor. He didn't have to wait long. In August 2019, amateur astronomer Gennady Borisov, working from his homemade observatory in Crimea, discovered a fuzzy object moving through the constellation Cassiopeia. It was on a hyperbolic orbit. It was outgassing vigorously, with a prominent coma and tail. It was unmistakably a comet, and unmistakably interstellar. It was designated 2I Borisov. Unlike Oumuamua, Borisov looked and behaved exactly like a comet. It had water. It had carbon monoxide, actually an unusually high amount of carbon monoxide. It had cyanide. It had dust. It was, in many respects, reassuringly normal. A dirty snowball from another star, doing exactly what dirty snowballs do when they get close to a hot star. They evaporate.
The scientific community breathed a collective sigh of relief. Interstellar comets existed, and they were comets. Unusual comets, to be sure. Borisov's carbon monoxide abundance was notably high, but recognizable, explicable, natural. And then 3I arrived. The evening of July 1st, 2025, the southern hemisphere, the Andes Mountains of Chile, a robotic telescope system perched high above the desert floor at the Rio Hurtado Observatory, scanning the sky with the relentless patience that only machines possess. The telescope was part of the ATLAS network, the Asteroid Terrestrial Impact Last Alert System. Funded by NASA, ATLAS was designed for one purpose: to find objects in space that might hit Earth. It operates 4 telescopes on 3 continents: Hawaii, Chile, and South Africa, each capable of surveying the entire visible sky multiple times per night. The system doesn't sleep. It doesn't take breaks. It photographs the heavens, compares each new image to previous ones, and flags anything that has moved. On that July evening, the Chile telescope flagged a faint smudge of light in the constellation Sagittarius. Magnitude 18, invisible to the naked eye, invisible to binoculars, visible only to sophisticated CCD detectors attached to research-grade telescopes. The smudge was moving, and it was moving in a direction and at a speed that the ATLAS software immediately recognized as unusual. The initial observation was reported to the Minor Planet Center, the international clearinghouse for positional measurements of small solar system bodies, at 0748 Universal Time on July 1st, 2025. Within hours, astronomers were scrambling to find earlier images of the same object.
The Zwicky Transient Facility at Palomar Observatory in California found it in their data from June 28th and 29th. Additional ATLAS observations were located going back to June 14th, and there was even a detection from June 5th that had been overlooked because the object was passing in front of the dense star fields of the galactic center, where faint moving objects are incredibly difficult to pick out. Amateur astronomer Sam Dean was among the first to identify these pre-discovery observations. He noted that 3I Atlas's path through the sky had taken it directly across one of the most crowded regions of the Milky Way, which is why it had escaped detection for nearly a month, despite being above the brightness threshold of multiple survey telescopes.
But once it was found, the trajectory told the whole story. This object was on a hyperbolic orbit with an eccentricity of approximately 6.2, far higher than Oumuamua's 1.2 or Borisov's 3.4. In fact, it was the most hyperbolic trajectory ever measured for any object in our solar system. The eccentricity was so extreme that the object's path through the inner solar system was essentially a straight line. It wasn't curving around the sun in any meaningful way. It was punching through. At the time of discovery, 3I Atlas was about 4.51 astronomical units from the Sun, roughly the distance of Jupiter's orbit, and moving at 61 kilometers per second relative to the Sun. That's about 137,000 miles per hour. For context, the fastest any human-made spacecraft has ever traveled is the Parker Solar Probe, which reached about 635,000 kilometers per hour, or roughly 176 kilometers per second, during its closest solar passes. But the Parker Solar Probe achieves that speed only briefly during its perihelion passages, and it's traveling in a bound orbit around the Sun. 3I Atlas was cruising at 61 kilometers per second in a straight line, bound to nothing, and it was going to get faster. As it fell deeper into the Sun's gravitational well, 3I Atlas accelerated. By the time it reached perihelion, its closest approach to the Sun on October 29, 2025, it was moving at 68 kilometers per second. That's approximately 153,000 miles per hour. And its perihelion distance was 1.36 astronomical units, between the orbits of Earth and Mars, but closer to Mars. Not terribly close to the Sun as comets go. Many solar system comets plunge to within a few solar radii of the Sun's surface. 3I Atlas kept a respectable distance, but it was close enough for the Sun's heat to start working on its frozen surface, and when that happened, things got very interesting very fast. Let's talk about what this object actually was, physically, chemically, because the details matter enormously, and they are unlike anything we have ever encountered. The first telescope to provide a truly detailed look at 3I Atlas was the Hubble Space Telescope. On July 21, 2025, Hubble aimed its Wide-Field Camera 3 at the object, which was then 277 million miles from Earth. The resulting image, processed by Joseph De Pasquale at the Space Telescope Science Institute, showed a teardrop-shaped cocoon of dust surrounding a solid icy nucleus. Because Hubble was tracking the fast-moving comet, the background stars appeared as streaks in the exposure, thin parallel lines drawn across the darkness by the motion of the telescope as it followed its target. The image was beautiful, but what mattered most was what it could tell us about the comet's size.
Hubble's resolution wasn't sufficient to directly image the nucleus, the solid body at the center of the dust cloud, but by analyzing the brightness profile of the coma and making assumptions about the nucleus's reflectivity, astronomers were able to constrain its diameter. Their conclusion, based on observations through August 20th, was that the nucleus was somewhere between 440 meters and 5.6 kilometers across. That's a big range. The uncertainty was frustrating, but understandable. The nucleus was tiny, distant, and buried in its own glowing shroud of gas and dust.
But even the lower end of that range, 440 meters, would make 3I Atlas's nucleus larger than Oumuamua's estimated size. And the upper end, 5.6 kilometers, would make it enormous by cometary standards. For comparison, the nucleus of Halley's Comet is about 15 kilometers long, but only a few kilometers wide. The nucleus of Comet 67P Churyumov-Gerasimenko, which was studied in extraordinary detail by ESA's Rosetta mission, is about 4 kilometers across. If 3I Atlas was near the top of its estimated size range, it would be one of the larger active comets ever observed at these distances from the Sun. Later observations by Hubble, conducted in December 2025 and January 2026, after the comet had passed perihelion and was receding from the Sun, finally managed to directly detect the nucleus through careful mathematical subtraction of the coma's brightness. The technique involved building a computer model of the coma, fitting it to the observed brightness distribution, and then subtracting it to reveal the residual point of light at the center, the nucleus itself. The results, published in a preprint by Man To Hoi and colleagues, confirmed that the nucleus was indeed massive. Combined with estimates of the comet's non-gravitational acceleration, the slight deviations from a purely gravitational path caused by outgassing forces, researchers calculated an estimated mass on the order of 44 billion kilograms. For a body of cometary density, that implied a diameter of several kilometers. Avi Loeb, never one to miss an opportunity to underline the extraordinary, pointed out that if you assumed a solid density, like rock rather than fluffy ice, the nucleus would need to be at least 5 kilometers across to account for the observed mass. That was, in his words, anomalously massive. But the size was just the beginning. The real revelations came from spectroscopy, the technique of splitting the light from an object into its component wavelengths to identify the chemicals present. The James Webb Telescope observed 3I Atlas for the first time on August 6, 2025. JWST is the most powerful infrared telescope ever built, and its near-infrared spectrograph, NIRSPE, is specifically designed to analyze the chemical composition of faint, distant objects. When NIRSPE's data was processed, the results were, in the carefully measured language of the scientific paper that followed, unexpected. The coma of 3I Atlas was dominated by carbon dioxide, not water, carbon dioxide. The CO2 to water mixing ratio was 7.6 plus or minus 0.3. That means for every molecule of water being released by the comet, there were nearly 8 molecules of CO2. This ratio was not just high, it was one of the highest ever measured in any comet at any distance from the Sun in the entire history of cometary science. It was 4.5 standard deviations above the trend line for long-period and Jupiter family comets.
In statistical terms, that means if 3I Atlas were a typical comet, the probability of seeing a CO2 to H2O ratio this high was less than 1 in 100,000.
There was one known outlier in our own solar system, Comet C/2016 R2, nicknamed Pan-STARRS, which also showed an extreme CO2 dominance. But C/2016 R2 was understood to be a freak of nature, a statistical curiosity. Finding a second such object and having it be interstellar raised profound questions about what conditions in 3I-ATLS's home star system might have produced such a CO2-rich composition. The JWST team, led by Martin Kortener of NASA's Goddard Space Flight Center, offered two possible explanations. The first was that 3I-ATLS had an intrinsically CO2-rich nucleus, meaning it was simply made of more carbon dioxide ice than water ice. This might indicate that the comet formed close to the CO2 ice line in its parent protoplanetary disk, the distance from the young star where temperatures were just right for CO2 to freeze, but water would remain liquid or gaseous. The second possibility was that there was some mechanism on the comet itself that was suppressing water sublimation relative to CO2. Perhaps the surface layers of water ice had been altered by billions of years of cosmic ray bombardment, creating a refractory crust that let CO2 escape but trapped water beneath it. Either explanation was fascinating. If the first was correct, it meant 3I-ATLS formed in a fundamentally different thermal environment than our solar system's comets. If the second was correct, it told us something about what happens to a comet's surface over timescales of billions of years in the radiation-rich void of interstellar space. But JWST found more than just carbon dioxide. The spectral data also revealed water vapor, water ice, carbon monoxide, and an unexpected guest, carbonyl sulfide, or OCS, a molecule made of one carbon atom, one oxygen atom, and one sulfur atom. Carbonyl sulfide is found in volcanic emissions on Earth. It's found in the atmospheres of Venus and Jupiter, and it had been detected in a few solar system comets before. But its presence in an interstellar comet added another line to the chemical fingerprint of 3I-ATLS's birthplace. Let me pause here and explain why all of this chemistry matters so much. Because if you're not a planetary scientist, it might seem like we're just listing chemicals. Carbon dioxide, water, carbon monoxide, carbonyl sulfide. So what? Who cares? Here's who cares. Everyone who has ever wondered whether life exists elsewhere in the universe. Comets are time capsules. They are among the most pristine objects in any star system, frozen relics from the era of planetary formation, preserved in the deep freeze of space for billions of years. When we study a comet's chemistry, we are reading the ingredient list of the planetary system where it was born. We are learning what raw materials were available, what temperatures prevailed, what radiation environment existed, what chemical reactions were taking place in the disk of gas and dust that would eventually coalesce into planets. And when we study an interstellar comet, we are reading the ingredient list of someone else's planetary system. We are getting a sample, an actual physical, chemical sample from a star we may never visit. It's as if the universe handed us a bottle of water from a stream we can never reach and said, "Here, taste this. Tell me about the mountain it came from."
The chemicals in 3I-ATLS's coma are the chemicals of planetary formation. Water is the universal solvent of life as we know it. Carbon dioxide and carbon monoxide are the building blocks of organic chemistry. Carbonyl sulfide plays a role in prebiotic chemistry, the chemistry that leads to the origin of life. These are not just random molecules, they are the raw ingredients of worlds. And 3I-ATLS was delivering them from a stellar nursery that might be billions of years older than our own. Now, let me tell you about the ground-based telescopes, because while JWST was providing the infrared view, other observatories were adding their own pieces to the puzzle. The Very Large Telescope, ESO's flagship observatory in the Atacama Desert of Chile, trained its spectrographs on 3I-ATLS in late August 2025. What they found was both reassuring and puzzling. The comet was emitting cyanide gas, CN, a molecule consisting of one carbon atom bonded to one nitrogen atom. Cyanide is a classic cometary emission, when solar ultraviolet radiation breaks apart the hydrogen cyanide, HCN, that sublimates from a comet's surface. It produces free CN molecules that glow at specific wavelengths, creating the characteristic blue-green color that many bright comets display. Finding CN in 3I-ATLS's spectrum confirmed that this was, chemically speaking, a comet. It was outgassing the same volatile molecules that our own comets outgas. But the VLT also detected something else: atomic nickel. Now, nickel in comets is not unheard of. In 2021, a team of Belgian astronomers made the surprising discovery that many solar system comets, including some observed at large distances from the Sun, showed traces of nickel and iron atoms in their comae. The mechanism was not fully understood, but it appeared that nickel and iron could be released from the surfaces of cometary dust grains at relatively low temperatures, perhaps through photodissociation of organometallic compounds. But in most comets, nickel and iron appear in roughly equal proportions. That's what you'd expect, because in the solar system, nickel and iron are cosmically abundant and tend to occur together in similar ratios. They are, after all, both products of stellar nucleosynthesis, forged in the hearts of massive stars and scattered across the galaxy by supernova explosions. In 3I-ATLS, the ratio was wildly different. There was far more nickel than iron, orders of magnitude more nickel relative to cyanide than had been observed in any other comet, including 2I-Borisov, which had shown relatively normal nickel abundances.
This was genuinely strange. Avi Loeb, in one of his characteristically provocative blog posts, pointed out that the nickel-to-iron ratio in 3I-Atlas was reminiscent of certain industrial nickel alloys, metals specifically engineered to be corrosion-resistant and heat-resistant. He was quick to note that this did not prove the object was artificial, but the implication was clear, and the headlines wrote themselves. Mainstream planetary scientists, predictably, were less impressed. They noted that the nickel-to-iron ratio in a comet's coma doesn't necessarily reflect the ratio in the nucleus itself. The coma is produced by sublimation and photodissociation. Complex processes that can preferentially release certain elements over others, depending on temperature, radiation environment, and the specific mineral matrix in which the metals are embedded. If nickel happened to be bound in more volatile compounds than iron, it would be released more easily at 3I-Atlas's distance from the Sun, creating an apparent enrichment that had nothing to do with the object's bulk composition. But here's the thing about anomalies. One anomaly is a curiosity. Two anomalies are a coincidence. But when anomalies start piling up, when you get 3, 5, 10, 20 things about an object that don't quite fit the standard model, you begin to wonder whether you're dealing with something truly new. And with 3I-Atlas, the anomalies kept coming. Let me list them. Not all of them. Loeb eventually compiled 22, but the ones that mattered most. The ecliptic alignment. 3I-Atlas's trajectory was inclined just 5 degrees from the ecliptic plane, the flat disk in which Earth and the other planets orbit. Interstellar objects can arrive from any direction. The ecliptic plane is tilted about 60 degrees from the plane of the Milky Way's disk, so even objects originating from the galactic plane would typically arrive at steep angles. A 5-degree inclination was, by some calculations, a fraction of a % probability. The anti-tail. From the very first detailed images, 3I-Atlas displayed a prominent jet of material directed toward the Sun, the opposite direction from a normal comet tail. Comet tails form because solar radiation pressure and the solar wind push dust and gas away from the Sun. A sunward feature, an anti-tail, can sometimes appear as an optical illusion due to the geometry of viewing angle, especially when a comet is near the ecliptic plane. But detailed analysis of the Hubble images from July 2025 showed that 3I-Atlas's anti-tail was not a perspective effect. It was a genuine physical jet, extending hundreds of thousands of kilometers toward the Sun, far more collimated, more focused, more beam-like than anything seen in any known comet.
The rotation axis alignment. Analysis of the wobble pattern in the anti-tail jet showed that the base of the jet was located within 8 degrees of one of the nucleus's rotational poles. And that rotational pole, in turn, was nearly aligned with the direction of the Sun. This meant that as 3I-Atlas approached the Sun, it had a stable day side and a stable night side, one hemisphere permanently facing the Sun, the other permanently in shadow. For a randomly tumbling comet, the probability of this alignment was about 0.5%. The persistent anti-tail after perihelion. Here's where it gets really weird. Before perihelion, the anti-tail was pointed toward the Sun, which was in the direction of travel. After perihelion, when 3I-Atlas was moving away from the Sun, the anti-tail continued to point sunward. But now that was behind the object relative to its direction of motion, and it was emanating from the hemisphere that had been the night side during the approach. This meant either there was a matching pocket of volatile ice at the opposite pole of the nucleus, a mirror image arrangement that would be an extraordinary coincidence, or there was some other explanation for the persistent sunward jet that standard cometary models couldn't easily provide. The symmetric jet structure. Post-perihelion Hubble images taken on December 27, 2025, and processed using a technique called the Larsen-Sechenina rotational gradient filter, revealed an astonishing structure. a sunward antitail plus 3 equally spaced jets emerging from the nucleus. The symmetry was striking. 3 jets 120 degrees apart, like the exhaust ports of some improbable engine. The mass budget discrepancy. During its perihelion passage, 3I.Atlas lost at least 13% of its total mass through outgassing. For a typical comet, this massive gas and dust release should have produced a prominent tail, a long, sweeping structure of particles pushed away from the sun by radiation pressure and the solar wind. But images taken after perihelion showed remarkably little tail. Where had all that material gone? The mass was leaving the nucleus, but it wasn't showing up where it should. The non-gravitational acceleration. Like Oumuamua before it, 3I.Atlas showed slight but measurable deviations from a purely gravitational trajectory. These accelerations were attributed to outgassing forces, the rocket effect of jets pushing the nucleus. But the specific pattern and magnitude of the non-gravitational acceleration had an interesting consequence. It fine-tuned the comet's closest approach to Jupiter, bringing it to within 53.6 million kilometers of the giant planet, almost exactly matching Jupiter's hill radius. More on that later. The CO2 dominance. As we discussed, the carbon dioxide to water ratio was among the highest ever observed in any comet. This alone placed 3I.Atlas in rarefied territory. The methane. Post-perihelion observations by JWST revealed robust methane emission. Methane is a molecule whose volatility lies between CO2 and CO. It is also a potential biosignature, meaning it can be produced by biological processes, though it can also be produced by geology and chemistry. The methane production rates relative to water were between 13.7 and 27% across 2 observing epochs. For a comet, this was unusual. Methane had been detected in some solar system comets before, but not at these levels relative to water. The nickel to iron ratio. As discussed, the extreme enrichment of nickel over iron was unprecedented.
The extreme polarization. Polarimetric observations, measurements of how the light from 3I-Atlas was polarized, showed patterns that were unique. The negative polarization values at certain phase angles were unlike anything seen in thousands of observed solar system comets. Polarization tells you about the size, shape, and composition of the dust grains in a comet's coma. Whatever was in 3I-Atlas's coma, it was scattering light in a way that no other comet had. The extreme polarization. Polarimetric observations, measurements of how the light from 3I-Atlas was polarized, showed patterns that were unique. The negative polarization values at certain phase angles were unlike anything seen in thousands of observed solar system comets. Polarization tells you about the size, shape, and composition of the dust grains in a comet's coma. Whatever was in 3I-Atlas's coma, it was scattering light in a way that no other comet had. The wow signal alignment. The arrival direction of 3I-Atlas, traced back into interstellar space, pointed toward the constellation Sagittarius, near the galactic center. This was within 9 degrees of the direction from which the famous wow signal, a powerful narrowband radio burst, was received by the Big Ear telescope at Ohio State University in 1977. The wow signal lasted 72 seconds, was never repeated, and has never been explained.
The angular coincidence was almost certainly meaningless in a scientific sense, but it was the kind of detail that keeps you up at night. Now, let me be absolutely clear about something. Listing anomalies is not the same as proving an extraordinary origin. Anomalies are, by definition, things we don't fully understand, and the history of science is littered with anomalies that turned out to have perfectly natural explanations. Pulsars were initially called LGM, little green men, because their regular radio pulses seemed too precise to be natural. They turned out to be rapidly spinning neutron stars. The cosmic microwave background was initially mistaken for pigeon droppings on a radio antenna. Gamma-ray bursts were classified for decades before their extragalactic origins were confirmed. In each case, the anomaly was real, but the explanation was natural. Planetary scientists reminded us of this loudly and frequently. Jason Wright at Penn State, one of the most respected voices in the field, pointed out that comets are inherently weird. He quoted the old saying, "Comets are like cats. They have tails and they do precisely what they want." Every bright comet that passes through the inner solar system turns out to be strange in some new way. The fact that an interstellar comet, one that formed in a completely alien environment, would display unusual chemistry and behavior was not just expected, but virtually guaranteed. Scott Manley, a well-known astronomer and science communicator, noted specific flaws in some of Loeb's statistical arguments, particularly regarding the trajectory alignment. David Kipping, an exoplanet researcher at Columbia University, pointed out that the population calculations depended critically on the assumptions you made about the population of interstellar objects, and that small changes in those assumptions could shift the numbers dramatically. Darrell Seligman, who led the first published scientific study on 3I-Atlas, stated bluntly that there have been numerous telescopic observations of 3I-Atlas demonstrating that it's displaying classical signatures of cometary activity. Astronomer Samantha Lawler emphasized that extraordinary claims require extraordinary evidence, and that the evidence presented by Loeb and his collaborators was absolutely not extraordinary.
Steve Desch, an astrophysicist at Arizona State University, went further. He systematically addressed several of Loeb's anomalies, arguing that Loeb's calculations about the tail length were 100% wrong because he has never understood that dust in the tail responds to solar radiation pressure rather than the solar wind. Desch pointed out that the solar radiation pressure on cometary dust particles is about 1,000 times stronger than the ram pressure of the solar wind, a basic fact of cometary physics that fundamentally changes how you calculate what a comet's tail should look like. So where did the truth lie? Was 3I/Atlas a natural object with some unusual features, as the mainstream consensus held? Or was it something more, as Loeb insisted, an object whose accumulation of anomalies, taken together, suggested a nature that our current models couldn't fully explain? The answer, I think, lies somewhere that neither side was entirely comfortable with. 3I/Atlas was a natural object, almost certainly. The evidence for outgassing, the detection of water, CO2, CO, CN, nickel, methane, and other familiar cometary molecules left little room for doubt that this was a body made of ice and rock, behaving in broadly cometary ways. But it was also an object from an alien stellar environment, billions of years old, with a composition and structure shaped by conditions we have never directly observed. Some of its anomalies were probably explicable by known physics applied to exotic initial conditions. Others might require new physics, or at least new models. And a few, the persistent anti-tail, the symmetric jet structure, the mass-budget discrepancy remained genuinely puzzling. The scientific community's job was to study these puzzles, not to explain them away, not to leap to alien hypotheses, but to study them rigorously and honestly with every tool available. And that is where the story of the deleted data begins. October 2025, 3I/Atlas is approaching perihelion. It is also approaching Mars. On October 3, 2025, the comet passed within 0.194 astronomical units of the red planet, about 29 million kilometers. This was extraordinarily close by astronomical standards. For context, Earth's closest approach to the comet would be 1.798 AU, nearly 10 times farther. Mars was, by a wide margin, the best vantage point in the solar system for studying 3I/Atlas up close. And we had hardware at Mars, a lot of hardware. NASA had 2 spacecraft in Martian orbit that were ideally suited for the task. The first was the Mars Reconnaissance Orbiter, MRO, which had been circling Mars since 2006. MRO carried the HiRISE camera, an instrument that had spent nearly 2 decades producing the most detailed images of the Martian surface ever captured. From orbit, HiRISE could resolve objects on the ground as small as 9 inches across. Now 3I/Atlas was much farther away than the Martian surface, about 20 million kilometers, so the resolution wouldn't be anything like that. But even at that distance, HiRISE would achieve a resolution of about 30 kilometers per pixel, 3 times better than what Hubble had managed from Earth orbit. It was the best close-up we were going to get.
The second NASA spacecraft was MAVEN, the Mars Atmosphere and Volatile Evolution mission. MAVEN's primary instrument was an imaging ultraviolet spectrograph that could detect specific atomic emissions, hydrogen, oxygen, carbon, in the coma of a comet. If 3I/Atlas was actively outgassing water, which breaks down into hydrogen and oxygen when exposed to solar UV, MAVEN would see it. And NASA had a rover on the surface. Perseverance, the car-sized robot that had been exploring Jezero Crater since February 2021, carried Mastcam-Z, a pair of cameras capable of photographing the Martian sky. If everything aligned correctly, Perseverance could capture an image of an interstellar comet as seen from the surface of another world. That had never been done before. ESA also had assets at Mars. The Trace Gas Orbiter, TGO, carried the Cassis color camera. Mars Express, which had been orbiting Mars since 2003, carried the HRSC camera. And China's Tianwen-1 orbiter, which had arrived at Mars in 2021, carried the HiRIC, high-resolution imaging camera. Between October 1st and 7th, 2025, all of these spacecraft were tasked with observing 3I/Atlas. This was a coordinated, multi-agency, multinational observing campaign of unprecedented scope. Never before had so many spacecraft at another planet been directed to observe a single transient astronomical event. On October 2nd, MRO turned away from Mars and pointed HiRISE at the sky. The camera captured a 3.2-second exposure, unusually long for an instrument designed to image a planetary surface from orbit. MRO is not well suited to long exposures. The spacecraft has a tendency to jitter slightly during extended imaging runs, which causes point sources to smear across multiple pixels. But 3.2 seconds was what was needed to capture enough photons from the faint interstellar visitor, and the HiRISE team accepted the trade-off. The data was captured, the observation was recorded. The bits and bytes containing humanity's closest image of an interstellar object were stored on MRO's solid-state recorder, waiting to be transmitted back to Earth via the Deep Space Network. And then the United States government shut down. October 1st, 2025, one day before the HiRISE observation. The United States Congress failed to pass a spending bill, and the federal government entered a shutdown. All non-essential government operations ceased. Federal employees across the country, including many NASA staff, were furloughed. NASA's public communications offices went dark. Press releases were postponed. Data releases were frozen. The agency's elaborate infrastructure for processing, calibrating, and distributing scientific data ground to a halt.
It's important to understand what this means in practical terms. NASA is not a monolithic entity. It is a sprawling bureaucracy with layers of management, protocols, and approval processes. Scientific data from NASA missions doesn't simply flow from spacecraft to public server in an unbroken stream. It goes through multiple stages of processing. Raw data is calibrated. Calibrated data is validated. Validated data is reviewed. Reviewed data is formatted for public release. At each stage, human beings make decisions, run software, check results, and sign off on the output. When those human beings are told to stay home because the government is shut down, the pipeline stops. The HiRISE data sat in the pipeline. So did the MAVEN data. So did the Perseverance data. The observations had been made, the bits existed, but no one at NASA was authorized to process or release them. Weeks passed. 1 week, 2 weeks, 3 weeks. The scientific community grew increasingly agitated. This was not like waiting for the results of a decades-long survey or a deep space mission with a leisurely timeline. 3IB Atlas was a transient event. It was moving through the solar system at 60+ kilometers per second. Every day it got fainter. Every day it got farther from the sun and from the spacecraft that could study it. Astronomers needed the Mars data to plan their follow-up observations, to decide where to point Hubble, JWST, and ground-based telescopes for maximum scientific return. The delay wasn't just annoying, it was actively costing the scientific community irreplaceable data. Avi Loeb was predictably the loudest voice demanding action. In a blog post on October 31st, he called the situation holding science hostage to the shutdown politics of the day. He argued that time-sensitive scientific data should be exempt from shutdown protocols, that the bureaucratic rules governing routine government operations should not apply to once-in-a-civilization observations of interstellar objects. When journalists asked him whether the delay might indicate that NASA was suppressing the data because it contained evidence of something extraordinary, something artificial, Loeb gave a characteristically quotable response. The delay, he said, is probably not a sign of extraterrestrial intelligence, but rather of terrestrial stupidity. That same day, Representative Anna Paulina Luna of Florida sent a formal letter to interim NASA Administrator Sean Duffy. Luna, who had been briefed by Loeb's team on the scientific significance of the Mars observations, urged the agency to release the HiRISE images immediately. She wrote that the data was of great importance to advancing our understanding of interstellar visitors and their interaction with our solar system. She noted that the HiRISE images offered roughly 3 times the resolution of the Hubble images from July,
and that the brightest pixel in these images would provide our most precise constraint on the object's size to date. Luna reported that Duffy confirmed the images would be released as soon as the government reopened. Unfortunately, due to bureaucratic reasons, they cannot until then. Meanwhile, the rest of the world was not waiting.
China's Tianwen-1 orbiter had captured 3I-ATLS with its HIRIC camera from a comparable distance. And unlike NASA, the China National Space Administration was not affected by the American government shutdown. The HIRIC images were processed, calibrated, and released through normal channels. Loeb noted in a blog post that the Chinese images showed the nucleus and a surrounding coma with a diameter of several thousand kilometers, confirming that the comet was active, outgassing, and surrounded by a substantial envelope of gas and dust. ESA also moved forward. The Trace Gas Orbiter captured the comet with its Cassis camera. Mars Express attempted observations but failed to detect the object, likely due to insufficient exposure time. The scientific community had partial data, enough to continue their analyses, but the most valuable piece, the HIRIS image, remained locked away. The government shutdown lasted 43 days. 43 days during which 3I-ATLS continued its headlong flight through the solar system, growing fainter, growing more distant, burning through its volatile ices in the heat of the sun. 43 days during which the optimal window for coordinating ground-based and space-based follow-up observations slipped away. When the government finally reopened, NASA moved quickly, relatively quickly by bureaucratic standards, to release the data. On November 19, 2025, the agency held a live stream event to share the first images from the Mars Observing Campaign. The event was watched by hundreds of thousands of people around the world, many of them drawn by months of speculation, conspiracy theories, and the irresistible question, what did we see? The live stream opened with NASA Associate Administrator Amit Kshatriya addressing the elephant in the room. "Let me address the rumors right at the beginning," he said. "This object is a comet, but this one came from outside the solar system, which makes it fascinating." He was pushing back, directly and explicitly, against the narrative that 3I-ATLS might be an alien spacecraft, a narrative that had been amplified by Loeb's public statements, by the government shutdown, and by the fertile imagination of social media. Then the images were shown. The HIRIS image, taken on October 2nd, showed a fuzzy white ball, the coma, the cloud of dust and ice being shed by the comet as it warmed in the sun's heat. The coma spanned the entire HIRIS field of view, but only the brightest inner region was detectable given the exposure time used. The nucleus, the solid body at the center, was invisible, lost in the glow. Spacecraft jitter during the 3.2-second exposure had smeared the image by several pixels, further limiting the resolution. That ball is a cloud of dust and ice called the coma, which is shed by the comet, Kshatriya explained. The image showed the visitor at a scale of about 19 miles per pixel. HIRIS principal investigator Shane Byrne, a professor at the Arizona University, noted that observations of interstellar objects are still rare enough that we learn something new on every occasion. We're fortunate that 3I-ATLS passed this close to Mars.
NASA also released images from MAVEN. The ultraviolet spectrograph had captured 3I-ATLS over 10 days starting September 27th, detecting hydrogen emission from the coma, a clear signature of water ice sublimating and being broken apart by solar ultraviolet radiation. This was crucial data. It confirmed that water was present in the comet's outgassing, even though it was a minor component compared to the overwhelming carbon dioxide. And then there was Perseverance. On October 4th, the rover had paused its geological investigations of Jezero crater and aimed its Mastcam-Z cameras at the Martian sky. The resulting image showed 3I-ATLS as a faint smudge, barely visible, easy to miss if you didn't know where to look. But it was there, an interstellar object photographed from the surface of another world for the first time in history.
Tom Stadler, lead scientist for Solar System Small Bodies in NASA's Planetary Science Division, put the images in perspective. We can image individual grains of sand on Mars because we have spacecraft standing on Mars, he said. But even our closest spacecraft to 3I Atlas, we're still 19 million miles away. The images were not stunning. They were not high-resolution portraits of an alien artifact. They were faint, blurry, hard-won detections of a small, distant object, obtained by pushing instruments far beyond their design specifications. But they were real, and they were ours. The real scientific treasure from the November 19th live stream, however, came not from the images, but from the context they provided. The high-rise image showed the coma from a vantage point very different from what Earth-based and Earth-orbiting telescopes could achieve. Hubble had viewed 3I Atlas from near the Sun-Earth line, meaning its perspective was nearly edge-on to the anti-tail jet. The high-rise view was a side view, looking at the comet from roughly the direction of Mars, which was almost perpendicular to the Sun-Comet line. This different viewing angle allowed astronomers to disentangle geometric perspective effects from genuine physical structures. And when Loeb analyzed the released high-rise image, he noticed something. The glowing plume around the comet was extended not just in the sunward direction, which would be expected from an anti-tail, but in the direction of motion, ahead of the object. It appeared as though something was preceding 3I Atlas along its trajectory, creating a luminous extension about 3,000 kilometers in length. It appears like there is something preceding the object that was previously confused with being in the direction of the sun, but is actually in the direction of motion, Loeb wrote. In previous images, like the Hubble Space Telescope image, the two directions were similar when 3I Atlas was heading towards the sun from far away. He posed the question, could this be a technological signature of illuminating or clearing the path from any hazardous micrometeorites that may cause damage to a technological object? Critics immediately pushed back. The 3.2-second exposure with spacecraft jitter could create all sorts of apparent extensions and structures in the image. The comet was moving fast through the field of view, and any smearing would tend to elongate the image in the direction of motion. Drawing conclusions about 3,000-kilometer physical structures from a single motion-blurred frame was, they argued, premature at best. And so the debate continued. Data was released, arguments were made, papers were published, and through it all, 3I Atlas continued its journey, oblivious to the controversy it had ignited on a small rocky planet 270 million kilometers away.
Let me now take you through what happened after the Mars flyby, because the story doesn't end with the high-rise images. It was only getting started.
On October 21st, 2025, 3I-Atlas passed through solar conjunction, the point where it was closest to the Sun as seen from Earth. At conjunction, the comet was separated from the Sun by just 2.59 degrees on the sky, making it completely unobservable from the ground. But spacecraft that were not aligned with the Sun-Earth line could still see it. NASA's Parker Solar Probe, which orbits close to the Sun and views the inner solar system from a unique perspective, observed 3I-Atlas from October 18th to November 5th using its WHISPER instrument, the Wide Field Imager for Solar Probe. SOHO, the ESA NASA Solar Observatory positioned at the Sun-Earth L1 point, also caught a glimpse. And the Stereo A spacecraft, which observes the Sun from an orbit slightly ahead of Earth's, captured colorized stacked images showing the comet moving through the inner solar system. On October 29, 2025, 3I-Atlas reached perihelion, its closest approach to the Sun, at a distance of 1.36 AU. That's between the orbits of Earth and Mars, roughly 203 million kilometers from the Sun. At perihelion, the comet was moving at its maximum speed, 68 kilometers per second, or about 153,000 miles per hour. Its surface was being heated by solar radiation, driving vigorous outgassing. The volatiles in its nucleus, CO2, CO, water, methane, were sublimating and streaming into space, creating a complex, evolving coma. After perihelion, 3I-Atlas began its long outbound journey. On October 3rd, it passed 0.65 AU from Venus. On November 6th, Europa Clipper, NASA's newest flagship planetary mission, launched in October 2024 and heading toward Jupiter, observed the comet for 7 hours from a distance of about 164 million kilometers. The Europa UVS instrument, the spacecraft's ultraviolet spectrograph, detected oxygen, hydrogen, and dust from the outgassing of 3I-Atlas near perihelion. The sunward viewpoint provided a downstream view of both the antitail and the regular tail. It was a remarkable observation, a spacecraft designed to study Jupiter's moon Europa, still years away from its destination, making a contribution to interstellar science purely by virtue of being in the right place at the right time. On December 11, 2025, 3I-Atlas passed less than 2 degrees from the half-moon as seen from Earth, a striking celestial conjunction, though the comet was far too faint to see without a telescope. By this date, the comet had moved more than 90 degrees from the Sun and was observable from the ground at midnight. Ground-based telescopes around the world began a new phase of intensive observation. The Hubble Space Telescope re-observed 3I-Atlas on November 30th and again on December 27, 2025, using its Wide Field Camera 3. The November 30th images showed the comet post-perihelion, still active, with a complex coma structure, including the persistent antitail and what appeared to be multiple jet features.
The December 27th images, processed with the Larsen-Sekanina rotational gradient filter, revealed that extraordinary symmetric structure I mentioned earlier. A sunward antitail, plus 3 equally separated jets emerging from the nucleus. The symmetry was almost too perfect. On December 19, 2025, 3I Atlas made its closest approach to Earth, 1.798 AU, about 269 million kilometers. This was the closest it would ever get to us, and it was still nearly twice the Earth-Sun distance. We were never in any danger from this object. It was a distant, faint smudge even at its closest, but it was close enough for JWST to take its most detailed spectroscopic observations yet. On December 22, 2025, JWST observed 3I Atlas again, this time post-perihelion, when the comet's heat-driven outgassing was at its most vigorous. The new spectra revealed something the earlier August observations had only hinted at: robust methane emission. Methane, CH4, was being released from the nucleus at significant rates. The production of methane relative to water was between 13.7 and 27% across 2 epochs of observation. Why does methane matter? Because methane is unstable. It's easily destroyed by solar ultraviolet radiation. On Earth, methane in the atmosphere is continuously replenished by biological processes: cows, wetlands, termites, rice paddies. On Mars, the detection of trace methane has been one of the most tantalizing hints that something, biological or geological, might be actively producing it beneath the surface. In the context of a comet, methane could be primordial, trapped in the ices when the comet formed. But the fact that it was being released preferentially after perihelion at rates that varied between observations suggested a more complex story. Perhaps methane was trapped in clathrate hydrates, cage-like structures of water ice that can encapsulate gas molecules, and was being released as the water ice matrix was disrupted by heating. The JWST team also found that the CO2 to water ratio had decreased somewhat compared to the pre-perihelion observations, about half as much or comparable between the 2 epochs. This suggested that as the comet's surface layers were stripped away by sublimation, deeper ices with different compositions were being exposed. The comet was peeling itself like an onion, and each layer told a slightly different chemical story. NASA's SPHX mission added still more data. SPHX, the spectrophotometer for the history of the universe, epoch of reionization and ices explorer, is an infrared space telescope launched in early 2025 to survey the entire sky. In December 2025, the SPHX team pointed their instrument at 3I Atlas and detected a complete suite of cometary ices: water, CO2, CO, and organic molecules. They described their findings as frozen samples from an alien stellar nursery delivered to our doorstep. The isotopic ratios, particularly the deuterium to hydrogen ratio in the water, differed from both solar system comets and the general interstellar medium, placing constraints on the temperature and ultraviolet environment of 3I Atlas's parent protoplanetary disk.
And then there was the age question. Where did this thing come from, and when?
tracing 3I Atlas's trajectory backward into interstellar space, accounting for the gravitational influence of the Sun, the planets, and nearby stars, astronomers determined that the comet originated from the general direction of the constellation Sagittarius, near the Milky Way's galactic center. Unlike Oumuamua and Borisov, which came from the direction of the solar apex, the direction our Sun is moving through the galaxy, 3I Atlas arrived from the opposite hemisphere of the sky. This was significant because it placed constraints on the comet's velocity relative to the local standard of rest, the average motion of nearby stars. The analysis suggested two possibilities. If 3I Atlas originated from the Milky Way's thin disk, the main disk of stars where our Sun resides, it could be about 4 to 5 billion years old, comparable to our solar system. But if it came from the thick disk, an older, puffier population of stars that formed earlier in the galaxy's history, the comet could be at least 7 billion years old, older than the Sun, older than the Earth, older than the first stirrings of life in our solar system. And a detailed analysis of its JWST spectral data pushed the age estimate even further. One study, published in early 2026, suggested that the comet formed in a cold, distant part of the early Milky Way up to 12 billion years ago. That's nearly as old as the universe itself, which formed 13.8 billion years ago. If this estimate is correct, and it carries significant uncertainties, then 3I Atlas condensed from a molecular cloud when the universe was less than 2 billion years old. It froze into a solid body while the Milky Way was still assembling itself from merging dwarf galaxies. It was ejected from its parent star system and has been drifting through interstellar space ever since, for longer than most of the stars you can see in the night sky have existed. Think about what that means. The ice in this comet, the actual frozen molecules that JWST detected sublimating in the Sun's heat, may have formed before the Milky Way had a recognizable spiral structure, before our corner of the galaxy had cooled enough to form rocky planets, before the heavy elements created by earlier generations of supernovae had fully mixed into the interstellar medium. This chunk of ice and rock is a relic from a fundamentally different epoch of cosmic history, and for a few months it visited our neighborhood. It flew past our planets, our spacecraft photographed it, our telescopes tasted its exhaled gases, and then it left. Now let me bring you to the climax of this story, the Jupiter flyby. March 16th, 2026, 4 days ago as I speak these words. 3I Atlas passed within 53.6 million kilometers of Jupiter, the largest planet in our solar system, a gas giant with more than twice the mass of all the other planets combined. The significance of this flyby goes beyond proximity. The distance of closest approach, 53.6 million kilometers, is, as I mentioned earlier, essentially identical to Jupiter's Hill radius. The Hill radius is the distance from a planet within which its own gravity dominates over the tidal gravity of the Sun. It defines the region of space where a planet can hold on to satellites. Jupiter's moons, Io, Europa, Ganymede, Callisto, and dozens of smaller ones all orbit within the Hill sphere. The Lagrange points L1 and L2, which are gravitational sweet spots where the forces of Jupiter and the Sun approximately balance, are located at the Hill radius.